Hello, everyone, and welcome to the sixth lecture of the information visualization course entitled Visual Analytics. So today we're going to be talking about visual analytics theory and motivation and designing models to accompany our visualization. You have already heard the term visual analytics a couple of times previously, and since visual analytics is one of the valid choices for your practical projects, I have decided to this year front load the visual analytics lecture a bit earlier. So we're going to deal with this topic today. So I've already given a definition of visual analytics in the first lecture, but let's go over it again because first lecture was kind of an intro with a flurry of new terms. Now we're a bit more mature with our InfoVis knowledge, so we might be able to put everything into better perspective today. So the official definition of visual analytics is that it's the science of analytical reasoning facilitated by interactive visual interfaces. So for us as budding InfoVis experts, the words analytical reasoning and interfaces, interactive interfaces are very, very important here. And let's repeat the kind of civil example, what visual analytics actually is. So imagine that a domain expert, for example, a scientist or a police investigator wants to solve a problem, which can be investigate a suspect's seized computer with lots of unstructured data or the incidence of a disease in a population. And unlike in business graphics and the, let's say, lower scale forms of information visualization, the solution comes from analyzing a large, very complex data set, which cannot be feasibly analyzed by normal means or by going over it in let's say, Explorer or File Explorer or Finder on Mac or whatever system you're using, Nautilus on Linux. So visual analytics builds a system that will allow the expert to analyze the data iteratively and interactively. So the iterativeness, we have already talked about the properties of insight. One of them is that insight is deep, and it indeed takes time and gradual approach to grapple with the data. And interaction, again, a very important component for any analytics and analysis task. We know that static visualizations don't really cut it for non-trivial data sizes. And the expert has to perform many subtasks to progress, and hands-on approach helps understanding. And our subtasks, we have already been over this in the interaction lecture as well. So those are the high-level, low-level tasks. Basically, the purpose is why we are opening up our visualization / visual analytics system. This will all remain valid for visual analytics. So we have also seen a couple of examples. So this is a visual analytics system tracking COVID. We have seen this a number of times already. And this one is called Tableau, and Tableau is probably the closest to a general visual analytics system there is, basically. So it's a very famous tool. It's a commercial tool that you can buy as a software as a service, and it will allow you to input your data, and they pride themselves in creating those very nice analytic dashboards for you. And Tableau has originated in the information visualization community, and as we discussed last time, the trellis plot was actually the original driving visualization to make Tableau happen, even though this is not really a trellis plot that we see here in this example. It has evolved somewhat. So at a glance, if you look at the typical aspects of visual analytics, or what you might have inferred from seeing the examples, so we see kind of like a dashboard style interface. We see that multi-view design seems to be very important, that there are multiple of those sub-windows in visual analytics systems, and that individual views are often very basic charts or plots, or they heavily utilize them. So here we basically see a bubble chart and some time series data. Here we're seeing a map, line graphs, and some figures. So all of those are basic plot techniques that we've been over in previous lectures. So those are definitely astute observations, but a true visual analytics tool goes deeper. It will involve an interactive and intelligent model of the data that will assist the user, because remember, we have talked about the data being complex, and so the user might need some help with the computer, which is able to do large number of computations very fast. And also, we need a very tight integration of visualization and the model through solid interaction design. So the user has to really have the feeling that they truly interact, that they are in the driver's seat, basically, that they're not just going through the motions that appear on the screen. So the concept of visual analytics is old, and there have been quite some predecessors to visual analytics. This is to name one example of maybe multiple pipelines that have occurred. So Fayad's paper from 1996, I think it was at a knowledge discovery venue, so at the KDD conference. There they have already started going from the let's say native properties of data analysis. So data, target data, pre-processed data, transform data patterns, which are all present in the data, to something human, which is knowledge, right? So they have added this interpretation and evaluation step to the patterns, like formally in a machine learning conference, because not normally, if you're going from data, and if you have evident patterns, then you have a successful machine learning paper, or you are able to detect those patterns, right? But this is an extra step. This is basically making the patterns accessible. So this is one of the forefathers or forerunners of visual analytics. And if you recall lecture 1, we have highlighted the difference between information visualization and visual analytics with the pipelines. So this is an InfoVis pipeline. Your data comes in, you process it, visualize it, people can interact, and then they will gain knowledge. This is also this pipeline slightly expanded. You could have already seen in Van Wijk's evaluation model. It's a bit more elaborate there, but it's pretty much the same principle. And indeed, with visual analytics, we are adding the model, which is there to assist the user, and this is the integration. But if we go over the pipeline in more detail, so we start at the blue arrow. This is how we arrive at our problem. Then we get our raw data, which will never be just ready for direct use. We are going to need to perform some data transformation that might involve steps such as cleaning, data selection, or feature selection, maybe integrating multiple data sets together, and other tasks. Normalization, maybe statistical tools over the data, as we have seen yesterday. PCA might require that, for instance. Then, of course, if we visualize the data, then we have to define our user interaction properly, adhering to the techniques described in lecture 4. That will allow us to explore the data and the model. And the model is built two ways. One is that we build the model directly from the data. So basically, so this arrow is the classic data analysis, data science / machine learning pipeline, that you go from data to build a model that you then update, and that will lead to knowledge, basically. So indeed, this part of model building is data mining, statistical techniques, machine learning, and possibly others. And this arrow is very important because this is model building from the visualization, so through user feedback and interaction. That's how techniques for visual analytics differ from classic machine learning, basically. Then basically the model is supposed to be able to refine itself throughout the process of the session. So it will change its structure, change its parameters, or at least refine them. or the user will be able to choose from a different model. This is there because of the iterative nature of the analytics process. Remember that we have discussed that the user will need some iterations over the data, so they're going to update the visualization quite often, and the model should basically chase the user's mental model and try to support their needs that they have right now during the analytics session, if that makes sense. So you start with some knowledge. That knowledge changes over time, hopefully increases, and the model should be able to give you relevant directions or data pieces based on your current level of knowledge. And for that, model and parameter refinement is of course necessary. If you would have a static model that is only trained once, then that wouldn't do, of course. And of course, the model will drive the visualization. So it will show the relevant data, or it will show the model itself if your model is interpretable, so that the user can open it. If it's a white box, then it will maybe, let's say, if we're talking machine learning, if your model is a decision tree, then that might be worthwhile for the user to inspect. If it's a deep net, then less so, because the deep nets are more black boxes. They are not very naturally interpretable if you look in the innards. But at the very least, they should drive the visualization. So let's say in the multimedia sense, if you have a set of images, this arrow means that the model will be able to recommend images that are relevant to the user right now based on the last interaction. That's what this arrow means, instantiated, for instance, in the domain of multimedia. And knowledge, unlike in the visualization sense, where all the knowledge comes from visualization, where you make the observation, so that stays. But of course, you are also interpreting model parameters and outcomes. So basically, this arrow is the visualization knowledge, the visualization pipeline knowledge. This is the machine learning slash data analysis, data science knowledge arrow, and the visual analytics knowledge. That's the entire point of visual analytics, is that your user will have a combined knowledge from basically both sources. And hopefully this synergistic knowledge will be larger than the sum of the two parts, or I mean, and hopefully it will be greater than even one of those parts separately. That one of those components is not doing all the work. And here we have a feedback loop. So new knowledge may lead to finding new data, or data selecting different parts of the data. If we originally had a very large data set that wasn't feasible, that it wasn't feasible to process it at once, or we can find new data sources, or maybe we can take a new look at the data somewhat. So basically, we go back to the beginning and restart our analysis. And this arrow is basically we are done. That's going to the end state for the sake of completeness. So now we've been over the visual analytics pipeline, and this is a very system-centric overview of key components of visual analytics. Notice how I've been mostly talking about what the system needs to do to support the user. But of course, the other component of this entire process is the user themselves. So why don't we add human reasoning, or why don't we model human reasoning, or provide something that to think about how the user is approaching our system. So the classic of the classics is the so-called sense-making process. It's work that is already 16 years old at this point, but but we humans haven't changed very much evolution or skill-wise when it comes to our analytics and reasoning. So we're gonna go over this process, and let's find out how the various stages of sense-making progress from data to the final presentation, or the deliverable and the end game result, basically. So the definition is that sense-making is structuring unknown data into a framework, enabling us to comprehend, understand, explain, attribute, extrapolate, and predict. That's the definition given by Piroli and Card in the paper that I have cited. And there are a number of loops. So there's the foraging loop, which is seeking information, searching and filtering it, reading and extracting it. There's the sense-making loop, which is iterative development of a mental model. So that's how you conceptualize the data that will best fit the evidence that you have in the data for your hypothesis. And then we have a reality/policy loop, which is putting the findings in a real world context. Sorry. So if we unpack the entire process from the bottom. So let's start with this small subloop that goes from external data sources. I think that's a self-explanatory term. That's your external data sources, your raw data that you have access to, and it goes to a so-called shoebox. So that's a term from basically casual photographic information or photography organization that people take a lot of photos on their vacations, and then before they get to sorting them, they will put them into a shoebox to sort later, basically. So it's already kind of pre-filtered relevant data, but it's not really structured. It still needs some processing though. So that's why we use the term shoebox here. I think it's a nice intuition, and it's exactly what it is. It's unstructured storage of data that is filtered based on rough relevance. So you just make a quick pass, and you just anything that could be potentially relevant you put in the shoebox. You discard everything else. And the processes are, well, search and filter. So that's indeed the process that you perform to put items into the shoebox. So we already see some relevant interactions in this part, and of course you can go back from shoebox to searching for more information. So especially if you get new hypotheses trickling down from the higher levels, that will drive the search for new data. One step above, we're going from the shoebox to the so-called evidence file. So the key thing is that Piroli and Card, the key component are the hypotheses. And I mean, for a good hypothesis, you should have evidence, right? So that's why it's called evidence file. So those are snippets of data or of information that are extracted from the information in the shoebox, either confirming the hypothesis, hence the term evidence, or leading to a new hypothesis. And I mean, your hypotheses are already well, evidences themselves of you building up insight, which is what you want to attain with visual analytics. And the processes here are that number 5 is read and extract. So you are placing relevant data items into the evidence file, so that you can view this as a secondary, more elaborate and detailed stage of filtering. So you take your shoebox, you really take a long, hard look at the data, and with each of those data instances, you spend some more time to see if it's evidence, or if it was just, I don't know, maybe circumstantial relevance, and you can discard it. And you can of course go back from evidence file to the shoebox, where based on your evidence, how you build your case, so to say, you might suggest it might suggest new patterns or even hypotheses, which will then trickle down to shoebox or even external data sources again. The next stage, one above, is going from the evidence file to a schema. So schema is a structured, so keyword structured, well-organized collection of information. So that is already, if a shoebox where your vacation photos roughly thrown on a pile, schema would be your photos selected, properly categorized, and tied to events that happened where the photos were taken, and basically already progressing to a real story of your vacation, basically. Schema is sounds like a very technical, very exact term, but it's more of an umbrella term in this sense. So it can have wide range of forms. So it can be your mental model. It can be a thought, basically. So the structure that you think up in your mind about your data, but it can be visualizations or preliminary visualizations that you do, maybe some mock-ups or some diagrams and flowcharts. And it can also mean that you went from raw data to nice curated data sets that are being stored and documented. So if you, for example, for a certain task progress to a benchmark data set, for evaluation, that is already considered a schema rather than an external data source, basically. And again, going over the processes, schematize means that you take your evidence file where the structure is still blooming, budding, so to say, and you put structure on the relevant information. And of course, you can given a schema, you can search for more evidence. So basically, if you place structure on certain information that you have had in your brain or in your evidence file, then you might start finding holes in your schema. So some parts are missing, and sometimes you might think that you have been too hasty um, in your original thoughts. So then you might want to go back to evidence file to see if there's evidence, and then, like always, you can also always trickle down to even more lower levels, basically. Then the next to last portion is the loop from schema to hypotheses. So that's your almost end game, basically. Hypotheses are tentative representations of the conclusions about the data, or they can be definite, or they can be tentative. Hence the parentheses here. So that's already some of your conclusions about the data. It maps to insight, right? Already. So I believe that there has been this much incidence of a disease in the population that I have investigated. You know, that's basically what is called a hypothesis in this regard. So we're not talking strictly the statistical terms. So like what hypothesis means in statistical testing, for instance. But it's basically the best synonym I would believe is conclusions / preliminary conclusions about your data. And the processes are that you build a case from the schema. So you formalize a theory based on the schema, which is itself based on the evidence one level below. And hypotheses, if you re-evaluate your theories, you will re-examine the schema, and you will maybe even form new hypotheses, which will then need their own proof. So that's the hypothesis in that instantiation is more like a hypothesis in the classic statistical sense. So you have a hunch, or you have something that you want to investigate, which will lead to going to the lower levels of data naturally. And then the final mini loop is going from hypotheses to what is called presentation. And presentation is basically the outcome of your work. So it doesn't have to be slides that you present to some kind of client or whatever, but it can be. I would say personally that deliverable is a better word. So that's the outcome of why you are commissioned to do your visualization / visual analytics project. So that's basically your hypothesis made accessible. So the process number 14 is called tell story, which I think is a very, very astute term. Based on the hypothesis and conclusion, you give it more of a, let's say, real life framework. You kind of frame it nicely to make it more presentable, more accessible to your viewer, basically. So this is so hypotheses are often highly technical. And this is where you go the extra step. And I mean, re-evaluate is again our top-down process that if you get consumer feedback, that will very often lead to re-evaluation of hypotheses or new hypotheses. More often than not, I mean, if you have done some software engineering, not necessarily even visual analytics, you know that software is never done. There are always patches, always some feedbacks, maybe some bugs being found. So this is the same logic here. So you get information from your customers, consumers, whoever they might be, and you want to and if you want to adapt further, then you need to go down again. So we have seen 16 points. So it's rather detailed, but I think it's a very nice structure of what we do in our brain.
Jan, 2 more minutes.
Yes. And so that gives us just enough time to wrap up sensemaking. So at a glance, the sensemaking diagram could give the idea of a waterfall, right? So this looks very, very, very waterfall-y. We're kind of it's kind of water rise rather than waterfall because it's going from down to up rather than the other way around. But I mean, assume it, mirror it by the vertical axis basically, and you have a waterfall, right? So going from external data to shoebox to evidence file to schema to hypothesis and presentation, and you only kind of go back in the case of a mistake that you need to reevaluate something, and you need to. So basically, you have failed in going up, so you need to go down again. And I would really like to stress that the contrary is the truth. The loops are the essential constructive part of the process, because you're learning to grapple with your data. So you are going back up between the bottom up and top down processes almost constantly, basically. So the users can really loop freely as per their needs. And Piroli and Card themselves say that top down and bottom up processes are invoked in an opportunistic mix. So what you need, you should be able to do. And I mean, of course, the system needs to support the loops. And the loops drive the entire analytics process. So really focus on the loops. Don't think for a minute that this is a waterfall, basically. So I think we can take our pause here. Do we have any questions so far?
For the moment, I don't see any questions in the chat.
Very good. So we're gonna reconvene at 5:30 in 5 minutes. Right. So let's resume our lecture. Previously, we have been talking about the visual analytics pipeline, which was from a system-centric point of view, and about sense making. So the complete process going from raw external data to the final deliverable of our visualization / visual analytics project. And for the sense making, I would like to once more emphasize that it's not a waterfall. So the loops are very important, and they are very important also in the visual analytics pipeline. But let's keep going. So one caveat that I would like to stress or emphasize: if you're going to be reading some of the optional reading for the course, please discern between the machine model as a component of the visual analytics system supporting analytics, so one of the components in the pipeline, and the user mental model of the data. Both are unfortunately just called model in the literature. So you always have to be very careful about the context if they're talking about about the model in the user's head, or the model that is an integral part of your visual analytics system. The interesting part about this is that, of course, the ultimate objective of visual analytics is to make these two perfectly in sync, right? That basically your visual analytics system will be able to detect exactly what you need to do for your analytics needs and purposes, and it will be able to serve you always the relevant data in the perfectly relevant, well-formed view. And basically analyzing data will be a perfect breeze, kind of. So we're not there yet, much like artificial intelligence is not a true intelligence yet, but it's definitely the ultimate objective. So there might be some value in overlapping the two terms, but I mean, for the time being, when we are still approaching this objective, it's best to discern between the two. So both are called model, and we cannot avoid that.
There are questions, actually.
Absolutely.
It was from earlier. May I ask them now? From before the break.
Okay, let's handle those.
Okay. Lianson asks, are there any limits to the communication between visualization and model as described in the visual analytics pipeline? In other words, is everything allowed from a design point of view?
Yeah, so that's a very good question, and I'm going to go back to, so for instance here, and yes, so how you instantiate this is completely up to you, right? So a true visual analytics model will be able to do this loops throughout the session, but it's never said anywhere that it has to be at least 20 times per minute, or it has to be n times per y, basically, or per x. So how you do this is up to you, and it's one of the interesting design choices if you're building visual analytics systems. So generally, it's believe that the more interaction that you allow, or like the more intelligent support you allow, the better. as long as you adhere to the good interaction design, which itself incorporates the rule of not overdoing it with unnecessary interactions. But if you're interacting once in a while, do you have a synchronous model? So basically, you will explicitly synchronize state between visualization and model in through the interactions, or do you have an asynchronous model that the user will give the model a task and it will ping the user back when it's ready? So that's completely up to you. So and what is weighted there, or what is evaluated there is does it make sense for the ultimate task? Because the key point about visual analytics is that there are very few general visual analytics systems for like basically all kinds of data. They are usually very directed at a certain task, a certain type of task, and they will need custom models. So you are completely free to do this, as long as these two are reasonably connected and the user can steer the analytics. Then you're doing fine. It's a fine visual analytics system if it's meaningful for the task. But there are no standards set in stone for this.
All right, thanks. Then IFA asks on slide 25,
Okay.
is the sense-making process something the user does when using the visualization, or is it also something we as makers should do in order to tell a story and or prove our own hypothesis with our visualization?
Yeah. If I understand the question correctly, and please correct me if I don't. There are basically two types of visualization that we are doing as the designers, right? So one is our intermediate visualization. So that's something to support our design hypotheses, and then actually three types. The second one is to support hypotheses. So if you have a user operating within your visual analytics system, then you're trying to give visualizations for excuse me, for saying, aha, now I see that what I thought about the data was right. And this is the, let's say, the deliverable. So that's the final visualization, that you're making it accessible to a basically to a wider audience. So building the hypotheses within visual analytics systems, which will itself involve visualizations, that's for the users of your visual analytics system. Or if you're designing a static InfoVis system where you're just designing a visualization, then those are the intermediate visualizations that you do yourself, or maybe mockups or progress work. And the presentation, the visualization in the presentation, the final visualization, that's when you kind of want to sell the idea of the visual analytics system, right? So you are creating visualizations to support the user, the analyst that is interacting within your system. That's this. And this is maybe creating a convincing demo, convincing deliverable, drawing users to your analytics system. If that makes sense, this answer. If not, please feel free to ask again or about details.
Okay, seems to be fine. So that has been answered.
Okay.
And then the last question from Liansen. Could you maybe give an example of user mental model of the data?
Well, the user mental model of the data. Yeah, it's a considerably vague term in definition sense, because that's basically whatever your user thinks about the data at a given moment. That's the user. That's kind of the user's mental model, right? So if you're let's say doing the going back to the example of the forensic investigator, that they have had some seized computer coming in from a suspect, and they will need to evaluate whether the computer contains data which supports the case against the suspect. Then in the user's mental model, there will be, let's say, roughly two categories that will be okay. So this is relevant. So this is relevant to the case, and this is not relevant to the case, right? So they will start shoeboxing. So they will go through, because this kind of data will always be contextual, right? So they will start shoeboxing, and they will throw in anything that could be possibly suspicious, because there is a big price to pay for false negatives, right? If you discard a data item and it was an evidence for a crime, then it's a big penalty for such an investigator. So it's better to throw in more data that is potentially relevant. So it's better to make false positives than false negatives in this case. So then you throw it into the shoebox, and basically the shoebox itself is so not, of course, the index of the data that is in there, because no user is gonna think that, okay, in my shoebox I have items ID 18, 36, 59, and so forth. They will say, okay, this is the relevant data, and I'm discarding the rest. Then I'm looking at it again in more detail to build the evidence. Then I have the schema, so maybe I can put them on a timeline to conceptualize the crime, how it could have happened, and how do fill in the missing pieces in my original hypothesis. Because I mean, here we are kind of starting with a hypothesis, right? That the person is indeed guilty. So we're trying to find evidence for that. So that's our starting hypothesis. And then I'm going to see if the person is guilty or not, or if I need more evidence, and I'm going to go back. But so that would be an example. But in the general case, the user's mental model is whatever the user might feasibly need, basically, and whatever he or she might think about the data at any given moment throughout your analytics session, basically. So that's why you need to talk to your users. I'm going to go over that later a bit. Does this make sense as an example? It's very general. It's a very general, vague term. Yes.
Yes, it's clear.
Okay. Any more questions?
For the moment, no.
Very good. So, of course, please continue asking them away if you have some, and let's progress from the sense making and this machine model versus mental model. So we have emphasized that interaction is indeed key or core for visual analytics. And in lecture 4, we've been over this science of interaction diagram, which nicely decomposes user goals and tasks and interaction techniques. So which components are relevant for visual analytics? And the answer might not surprise you. It's actually all of them. And the reason why it's all of them is because visual analytics needs to support all of this. So in general, if you have a domain problem, you need to allow your user to go from the raw data to their hypotheses. So all of this will evidently require various of those interactions, right? So from low level to high level, and select, explore, reconfigure, encode, abstract, and elaborate, filter, connect, all sound relevant, right? I think it's self-evident. So there's a very broad scope of things you can and should do in visual analytics. The palette is pretty much unrestricted. And if we go further from so we have it on the one side, we have had the machine, so we have had the pipeline, and on the other we have had the human. That's the sense making part of the entire process. So in a work by the people from Constance, Dominic Zacha and Collective, they have tried to integrate the models, basically, to make the final visual analytics model that will involve everything. So this is so here, these three, you see that we have this is pretty much the visual analytics pipeline redrawn. We see those arrows. We see the arrows between visualization and model, the core of visual analytics, but we're missing the knowledge, and the knowledge has been expanded into human and human actions that happen that basically happen throughout all the stages of the analytics process. So this is kind of like a first step towards integrating the computer with the human into one model. So the actions here are kind of what we have already talked about. So preparing the data, model, designing the model building in the automatic sense, doing the visual mapping from data to visualization. Then it's the model usage, and model to visualization mapping. So, and of course, manipulating the visualization. Note the difference between full and dashed lines. So the full lines are meant to be actions by the users, and the dashed lines are meant to be actions by the designers. So obviously, the user is not going to design how the data is going to go into the model. That's what the designer of the visual analytics system does. And but on the other hand, the user manipulates the visualization, they use the model, and they are also preparing the data, because maybe not in the let's say normalization or statistical or data science technique sense, but any visual analytics system in applied domains such as medical sciences, the forensic investigator, or maybe news and marketing, they stem from a data set that was prepared or collected by the domain experts themselves. So that's what's meant by preparation here. And I mean, the human finds nuggets of knowledge in the data, right? So they're going to inspect the data, observe the model, and observe the visualization. So this is a bit of an expansion, and this is the fully expanded model. So this is to date the most complete model of visual analytics involving both the computer and the human. And we don't really have to go over. So this is pretty much a visual summary of what we have talked about so far. This was, as I said, this is the InfoVis pipeline, is the top part of the original visual analytics pipeline. The bottom one is called KDD process, or we can call it data mining or machine learning. So basically the statistical data processing, data science approach to finding knowledge in data. And knowledge has been expanded into basically four more sub-steps that lead towards knowledge. And all of this is pretty much a simplified version of the sense-making loop. So it's not something that we need to learn anew. That we have our action and finding from the previous slide, and we have insight and hypotheses, which are, in my opinion, very vague and synonymic terms, both of them, because we have mentioned that hypothesis and can be conclusions about the data, and it can be a hunch about the data as well. So the boundaries between these are super foggy, even to me as a reader of this paper, and that will go to knowledge. But there are of course also works that say that insight equals knowledge. So this is in my opinion a bit foggy. But what's the takeaway here is this is the latest fully expanded visual analytics pipeline involving the human, as accepted by the visual analytics and InfoVis community. Hence, it has a place in this course. And B, it's all right if you say, okay, this is basically the sense-making process on top of the visual analytics pipeline, and the stage which you're at. So like if you look at the sense-making process steps, so the stage that you're at will of course drive your interactions with the visualization and therefore with the model. That's all you need to remember. So this is an attempt at a comprehensive visual analytics model that will integrate several core previously isolated ones. So I'm not going to ask you to be able to draw this from memory, but it's a comprehensive model. Now, let's discuss the usefulness of all this, actually. So one could think that visual analytics theory equals just adding more and more arrows to InfoVis with each successive paper, right? So we have started with something that's pretty clear. There's the information visualization pipeline. And now we're adding models, now we're adding arrows everywhere. We have emphasized that loops are very important. So, I don't know about you, but this was definitely my way of looking at things when I started delving into visual analytics myself, which is a while ago, and I had this conclusion about all this even without knowing the final fully expanded pipeline, without knowing this. So this has came into existence after I have started my visual analytics journey. So because this at a glance is super confusing, right? So that leads to a question. So is it really useful, right? So the users can keep going between phases as they please. There are super vague terms such as insight or knowledge that are very difficult to quantify. We have seen this especially here, that this is the differences between these are very foggy. So yes, it makes sense. So the users will want some knowledge, insight, understanding, is another word, but we don't really know what it means. We cannot quantify it, we cannot measure it, and so all we know is that that if we ask the user, yes, do you think it was insightful? So yes, I have learned something, then we have succeeded. But it's a bit of a binary evaluation, right? And even if we adhere to the insight-based evaluation protocol that we have mentioned in the fourth lecture, which is very useful, it's still not very exact, right? And can be a bit laborious to conduct. So, and the overall advice seems to be very vague as well. So it's do whatever the user might need and connect everything with everything. Well, I would actually make an argument that it is useful. I mean, that's hardly a surprise. Otherwise, I would not waste your time with 30 slides on visual analytics theory if I didn't think it was useful at all. Even if it might need a second glance, and even if it might need you to look at the diagram and kind of digest it, diagrams rather, and digest them, in second, third wave maybe. Well, iteratively, as we said, that's the path to insight, right? Because I would argue that it gets you into the right design mindset. That both on the system side and the user side, it is very complicated. There are many aspects, and visual analytics indeed is very highly multidisciplinary. It involves elements of, well, InfoVis to design nice visualizations. You will need data science to design models that support the analytics. You will need a good portion of software engineering, because so that means getting good requirements from the user, and visual analytics systems are complex code-wise. So if you start coding a visual analytics system, even a simple one, good luck making it under thousands of lines of code. It always blows up very, very fast. And if you don't adhere to some good software architecture, then it will come to bite you. As I have learned that number of times before. Sometimes you even need to delve into high performance computing when you're tackling large data sets. I mean, of course, if you work with data in modern toolkits such as NumPy or scikit-learn, lots of that work is done for you, but you still need good intuition about what's going to work, because you're very constrained by the interactivity. You need your interface to be responsive. Otherwise, the user will be very annoyed and will leave your system. And it also needs people skills to an extent, because you need empathy and you need communication. So visual analytics is about the ability to think like the users and empower them with analytics in their own domain. So as I discussed earlier, it is related to one of the questions that we received, how do you design the modes of interaction, right? So are there any guidelines how many interactions you need per minute or per unit of time? And it depends on the domain of the user. And you are, of course, fighting an uphill battle, because your users will know more about the problem than you do. If you want to make a visual analytics system for forestry, it has to be useful for forestry experts, and you're not a forestry expert. So me personally, I find this part of the job very very interesting, because you get to talk to many interesting people, and you learn a lot about various disciplines. So this is definitely not something that you can just program yourself from your own standpoint, and it will just work. It really involves much communication with your users, or with your audience in general. And what about the design takeaways from the theory? So we're going to progress to the second part of the lecture later, which is going to be more about the models, like what the techniques are. But what are the takeaways from the theory? So in visual analytics, if you make challenging data accessible, that's a perfectly valid objective for your system. So if you get an assignment that says, okay, so we have large data sets in our domain context, and we don't know what to do with them because we cannot process them, make it happen for us. And you achieve that is perfect. So if you actually contrast this with pure information visualization, this would kind of be a Q-type error there if you use the trifecta checkup, because your visualization doesn't make a point. it just shows the data. You have your data and you show it, or making it accessible, showing it in visualization. And but in visual analytics, it's that is all about allowing the users, the analysts, to come to correct points on their own. We're not telling a story. So visualization should, if you're telling a story with visualization, then that's a good way to approach that. But with visual analytics, people should make their own conclusions, basically.
Oh, sorry to interrupt. Two
Yeah.
more minutes. I just wanted to say.
Okay, no problem. Thanks. And so you can still use trifecta in checkup in visual analytics, but I would say that Q in visual analytics means that you have provided sufficient interactive support for meaningful high-level tasks, basically. So then you have answered your Q. So that's a bit of an instantiation of trifecta checkup in the world of visual analytics. And regarding the usefulness, so this is roughly, if you kind of superimpose classic InfoVis in the final sense and visual analytics on the sense-making process diagram, I think you would have something like that. So the hypothesis is kind of like an exchange point, or that's the intersection of the two. But with visual analytics, you're trying to do all of this for the users to come to their own hypotheses. But if you're producing the final visualization, or things like that you're seeing, for example, in the article on junk charts, or you're just seeing visualizations, infographics in your favorite media outlet, then basically the visualization does this. So all of this is done previously to the visualization. So you kind of process your data internally, you kind of build the shoebox evidence file schema. So you still go over all these steps, but you do this as the designer of the visualization. And this is the final step that is revealed by the visualization. This is a very simplified view, so I have deliberately chosen the words the final visualization, not InfoVis here, because of course there are analytic visualizations as well. So it's not InfoVis, it's the final visualization for or more like in the business graphics sense, or in the kind of one directional interaction sense, if that makes sense. And of course, like one of the things that we have discussed in the slide where I was actually questioning the usefulness of visual analytics. Yes, fully supporting all the connections that we see on the pipeline or in the sense-making process is very challenging. It's a very widely recognized challenge by the community, and not all visual analytics systems do support everything. So they score 100% on the Zaha diagram, on the final fully expanded pipeline, that they will just go over them and check all the arrows, and they're saying, okay, perfect, we are supporting this fully. So that's very tricky. And then I'm going to finish this slide, and then we're going to go for the break. Don't worry. I know that I might be going over the 2 minutes in this instance, but it's best to finish the point. And the important design takeaway is that visual analytics systems are highly domain specific and task specific. I mean, I have hinted at this a couple of times during this presentation already, but it's worthwhile to highlight it again now. There is no single visual analytics system best across all domains that work with data in any capacity. And also none of the visual analytics systems really supports all fathomable high-level analytic tasks. So there is no silver bullet, basically. So you will always design visual analytics for certain domain, certain tasks within the domain, and you are going to make trade-offs to support your tasks and basically draw clear boundaries what you can and cannot do. And it's up to your users to judge whether such a system is worthy or not. Tableau is the closest to a general visual analytics system, and I mean we're not going to see later. We have seen this before, so this is a bit of a continuity error. I'm going to correct that on the slides. But even though that one is the most kind of general of the systems, that is not the standard. And if you think about it, both of these aspects greatly simplify the problem. So it kind of eases us from having to support all the 27 of arrows, or how many there are, to basically choosing our battle, which I also think makes visual analytics quite interesting. Let's take a break, Now it's 58, so I'm going to come back at 03. See you in 5 minutes. All right, so in the previous section, we've been talking about the design takeaways from the VA theory, but are there any questions at the moment from the previous part?
Yes, there's a question from Jansen.
Mm-hmm.
He asks, what is the most appropriate way to store insights you get from a VA system? Is there a formal way to incorporate them in your visualization for further future analysis?
Yeah, that is a very good question, and it's an open scientific challenge, especially when in the context of collaborative visualizations and visual analytics systems. If you need to share those insights, currently, I believe the best system is, and I believe means that it's the state of the art, not my personal beliefs, but what the conclusion seems to be so far, is that you just save the state properly. So so if another person or you yourself want to continue with the analysis, that basically the system properly stores where you left off. Plus, it allows the classic notes. So basically, the oldest archival system in existence is still the best. So because those insights are can range from very simple observations about the data to complex hypotheses, the best way to store them is free text, because generally the insights are so I mean the kind of counter question could be, so what if you have hundreds of insights for your analysis? uh, it's still the case, because what is considered insight is conclusion about the data. So if you have some kind of intermediate snippets, so those should be saved in the state itself. So basically, if you progress to a very nice summary visualization working with your model, then basically lots of that insight, lots of those sub insights, or even some let's say higher level insights, are captured in the visualization itself. So basically, the state of your analytics system is a snapshot of your level of insight. I think the combination of the two, so the state plus free text notes, are the standard so far. And but you can also think about the uh, about how it works, works nicely with, let's say, Google Docs. It's not a visual analytics system, but I mean, if you have collaborative writing, then people are just able to stick comments in different parts of the text to collaborate. And I mean, this kind of UX design is applies to visual analytics as well. So that's a nice example. Being able to stick comments, notes, yeah, the classic, I would say. So I hope that answers the question. Are there any others, or maybe a subsequent question?
Oops. At the moment, there are no other questions, and it's clear. Thanks.
Okay, very good. So let's keep going on with the lecture, and yeah. So basically, this is also a visual summary of what I have been talking about before. Of course, the entire pipeline is important for visual analytics, but if you want to a true visual analytics system, then basically you should have very good implementation for the core part, which is the visualization, the model, and the tie between the two, and the ability to adapt them. So this is a bit of a visual summary of what I have been talking about previously already. And so now, if we correlate visual analytics with the theory we have been over in the previous lectures. So the good thing is that we already know how to create interactive multi-view visualizations. So that's exactly what visualization in the VA pipeline is. So you adhere to good design practices that we have learned previously, and you're golden when it comes to visualization. We also know how to evaluate visualization. So and that theory applies to VA too. So I would say that for visual analytics, it's especially useful if you have insight-based evaluation. So if you have a protocol, I mean, so if you have the open-ended protocol where people are allowed to speak their mind throughout the analysis, you record the timestamps, and then you're monitoring what the domain experts, which should be your test users, achieved in the session. And for evaluation, remember that Q in trifecta checkup becomes, did we support the user in formulating and supporting their own hypotheses? It's not just, it's not a question really, but it's the support. It kind of transforms. And the other parts of evaluation that we've been over are perfectly valid for visual analytics, just as well as they are valid for InfoVis. If we look at the sense-making part, I would say that sense-making is a useful decomposition of different stages from raw data to crisp hypotheses. So I would say that thinking in the sense-making sense helps identifying the key high and low-level tasks from the science of interaction by Pike. And it will also help you design the interactions accordingly, which is very important. And the right side of the fully expanded VA pipeline by Zacha and collective conceptualizes user behavior. So there, the key takeaway is that you can and should role play as the user throughout all stages of design. So whenever you try and implement something, always put yourself in the user's shoes. So that's also the empathy that I have talked about as one of the 5 key disciplines for visual analytics. And the fully expanded version of the pipeline gives you a rough schema for that. So like it kind of gives you a bit of a scenario how to role play. So you have those actions, you have those kind of key steps towards insight. So you can kind of model that formally. If you have nothing else to go on, especially in the domain, which is not your domain of expertise, as we discussed. VA is very domain specified. So you might need to fall back on a general framework there. And so this was the theory part of the lecture. So how do we go about actually supporting an interactive visualization with a model? So that has so far been the key missing ingredient. So we circle around it. We are saying model. So what is it actually, right? And before we get into that, so the key part is integrating both. So the model should be designed alongside the visualization already. So it's not that, okay, that you start with the problem, that you design the visualizations, and then you're going to say, yeah, okay, so now what model do I choose to support this? No, what you need to do, and I mean this aligns perfectly with what we have discussed in lecture 3, is that we design visualizations with a purpose, right? So we're always thinking of the high-level tasks and our data, and we're designing the visualization alongside with the interactions. And if you do this systematically, this will nicely define the interface between visualizations and between the visualization and the model, and it will define the requirements for it. Then you basically design the model, and that will implement this interface, and then you iterate on this as you progress from the rough design to final implementation. And as we discussed before, waterfall planning never works, so we're doing all these iterations. So we think of the purpose, design our visualization plus the interactions. Those interactions will form the interface between the visualization and the model, and then we design the model, and we kind of keep going like that until we achieve something that is passable, or that we are satisfied with. It really shows if the design has been iterated upon, by the way. So that's something useful also for the practical projects. Do we have a question?
Yes, Gian asks, if you role play throughout the whole design, should you only user test at the end? Or also already for your individual stages when designing?
That's a very good question. So in the ideal world, you would be able to design throughout the stages, but generally this is not very feasible, because especially for the insight-based evaluation, you want your users to be experts, and they are very expensive to get, right? So they won't have the time, even if you design it for them. That's a bit of a kind of practical remark. So yes, intermediate testing is a very good idea, if you have let's say simplified subtasks that are generalizable to basically your fellow developers or to people that are not involved with the domain, maybe you can create some smaller benchmark tasks or smaller tasks that even insight-based ones where people kind of try to complete it with your visualization, and then you use the results of these to drive your further design. So that's always useful. So but it's not a necessary part. So I mean, you might notice that this rough pipeline or rough recipe that we give here is similar to agile programming, right? Where testing is core in each iteration. Here it's a bit more foggy, but if you can do it, then testing is always a good idea.
All right, thanks. That makes sense.
Okay, perfect. So going further, because so we have talked about that we should design the model alongside the visualization, and especially alongside the visualization and interactions, because if you do that properly, even before you start selecting your model, then you will have already taken care of this. So you will have your visualization with the interactions, so that's this. And given that you have the interface hanging down from the visualization, so you will tie the model to those interactions. And of course, each of those interactions will probably, or many of them, not necessarily all of them, will require some response from the model. So if you do this right, systematically and iteratively, if you really do this systematically, then you will have taken care of this, which is almost the entire or the majority of the visual analytics core. So that's why it's a useful thing to design like that. And again, going over the good software practices, I promise that we're going to get into the model techniques, at least an overview of the model techniques soon. But it's still good to give you the good, let's say, software practices that pertain to visual analytics, which could be useful also for your practical projects. What you need to do is you have to shift the heaviest load of to pre-processing. So basically, you want to do as much work as you can in this part, computational work in this part of the pipeline, right? Which is the one, the pre-interactive part of the pipeline. And you will construct your model in general sense to maximize lookup operations. So the computed data should pretty much already be there. The maximum of that can be there, it should already be there, because lookup operations are very fast and they don't hamper interactivity. So if you have mostly lookups, then you will be cooking when it comes to responsiveness. The model should be in the backend. So if you're following the stack of the practical sessions, that should be in Python / bokeh. Ideally, all the data operations computationally should be performed here, even the dynamic ones that require interaction from the users and therefore cannot be fully pre-computed. And there should be efficient communication with the front end. So you will try to communicate with the item IDs or the data instance IDs, rather than that you're going to be keep sending the entire data instances up and down all the time, and basically efficient communication like that. So you will always, with your API or interface, you will always send as little information as possible while still drawing the correct things on the screen, basically. The front end or the JavaScript part should pretty much be just the visualization. So, and just the visualization means that it just fetches the representation from the model, which is in the backend. It will just show the data which has already been digested, and there's going to be rudimentary interactions. So of course, like highlighting something on hover or selecting something, that's of course an interaction done in the front end. That's where it belongs. But you shouldn't really do any data computations. And you also should keep the state of the system as synchronized as possible. You're going to save yourself a lot of headaches, because sometimes it's very tempting to keep a lot of the state in the front end only, or like that you have a backend state and front end state which only have a very small overlap, because it kind of makes sense. But this becomes a real pain when you're kind of designing new interactions, and it's not very modular. So it's always good to have to kind of, even at the cost of less efficiency in the communication, it's still good to synchronize the state as much as you can, because then you can design new interactions better. Sometimes it happens that you have asynchronous state, you keep something in the front end, and then you actually design a new interaction which is meaningful. But wait, for that you need that same interaction in the backend. So then you design something quickly to pass the information, and then you're going to have 80 of those little methods that were kind of backdoored there to synchronize the state, and it becomes a mess. So as default, try to keep the state synchronized. And if you need kind of different variables or not send something between the model and visualization state-wise, have a really good reason for that. That's my let's say software advice. If you do this, then you're also making saving state possible. So like related to Eliansen's question from before, you know, how do we keep insight? How do we allow for continuing the analysis or saving the state? If you keep the state in the backend, then it's very easy to save it and restore it when you want to start a new analytics session later. And also, it's very useful to go over supporting the interaction. So we have talked about interactions being core to visual analytics. So let's go over the 7 interactions by Yi et al. And see what it means for the stack as for the abstract stack as designed here. So first we have select. That's actually one of the simple interactions. There it's very easy to just highlight the items in the visualization and keep the state. So take note of which items are being selected. And this is pretty much an interaction that is always used in conjunction with the other interactions. So the information about what is selected will drive the other interactions. Explore is a typical interaction where you call on the model to show something else than what's on the screen or been seen in the near past, basically. So in practice, if you have some kind of filtering scheme in your model, which you should probably, or an index, you will do an inverse of filter combined or replaced by a randomized selection. Because if you're searching, if you're filtering, you have some, I don't know, data about your trades in across the Netherlands, and if you search that you want data for Breda, then the inverse is not Breda, which is most of the data, right? Probably. So there you might need to do the filter, so the not Breda filter, and then you need to do some randomized selection, possibly to show something else that is digestible, that is not cluttered on the screen. So that's why we have a combination of the two. Reconfigure, if it's trivial, if it's just, I don't know, reordering the axes of a parallel plot, then you can do this in the visualization only, just reshuffling the display, possibly synchronizing state with the backend, and you always want to rely on the model to pull up data that are not on the screen. So sometimes it might be tempting to preload a lot of data or kind of like to stretch the kind of the browser cache as much as possible, but rely on the model to pull up data that are not on the screen that should be visible at a given time. If you reconfigure, for example, sorting, if it shows a different portion of the data set, if you sort something, then pull this up from the model efficiently. If we have encode, so encode means having more data structures, efficient data structures that are visualized. So you're just fetching a different representation from the model, and the visualization will re-render the data. That's how you should approach this. Then we have abstract elaborate. So this is kind of related to the concept of aggregation and hierarchy. You need to be zooming, and in all but very, very trivial dataset cases, the zoom hierarchy will need to be pre-computed and fetched from the model. So you will not be able to compute aggregates on the fly, which is understandable, right? And finally, we have filter and connect. So a filter will rely on an index, which is again part of the model. So we have been over this kind of when we were talking about explore. If you have tabular data, then a simple database query might just do. So if you're just searching data in your database, your data is a table. So instances with attributes of variable types that we have discussed previously, going from categorical to ratio. In case of more complex data, so we're going to go over text and multimedia analytics I think in 2 weeks. So there it's a bit more difficult. So there you might need some efficient index. But you will have a part of the model that will take care of filtering and searches, of course. And connect is generally good if you can make it easy in a visualization. So basically, if you just select, but if you're maintaining the select states properly, then you're just going to say, okay, I'm gonna have select as a, let's say, global-ish variable, or like it's going to be a variable kept in the master. In, let's say, the master class of the multi-view. So if you have a multi-view visualization, so you will keep state up. And it will say, okay, I have updated select, so please trigger re-rendering, and I am now going to highlight the respective data items in all of these views. That's an easy way how to do this in front end. I'm not now sure about the D3 support for this, but I'm very sure that you can do this in React.js at the very least. And so this provides an efficient command structure to highlight specific IDs across the views. Basically, this can be done in a visualization. And so if you look at it from a global perspective, so free interactions rely on the model very heavily, and they present a computational challenge in live user session because they hinge on dynamic user choice. Those two, especially the two, especially two of them, explore and filter, because there, of course, you cannot fully pre-compute what the user will want, because the user will say, okay, now I want pictures of birds. So you need to react to the actual need. So you need to have an efficient structure that will be quickly able to pull up the query. Abstract elaborate is also quite challenging in this regard, but that one can be front loaded to pre-computing, right? So you pre-compute a meaningful zooming structure. So that's the hard part being done, and then the user will be just pressing the mouse wheel button, scrolling rather, and they will be able to dive into different parts of the collection. So that should be quite doable already. But I mean, they will be looking at different parts of the collection at different moments. So you have to be able to fetch subsets of this hierarchy that you have built efficiently. There are three interactions that need a model to supply efficient data structures. So they will need to quickly pull up data for quick visualizations. Those are reconfigure, encode, and connect. And I think that this nicely illustrates, if we take this kind of software design perspective, it nicely illustrates the need for tight integration between model and visualization. How are we doing on time? I think it's approaching, right? The break.
Yeah, it would be like 5 more minutes, and we have like a question. I'll just ask you now, what's the most efficient way to keep the state of the system as synchronized as possible? Could you maybe give an example?
Yes. So basically, what we're doing here is that we keep. I'm not sure I have to go to this previous slide, but let's go here. So what you want to have is you want to have some kind of variable structure in your backend. So if you're using objective-oriented design, it could be a class, or it can be a dict if you prefer that in Python. So pick your poison. So basically, just kind of like a data variable that conveys structure. And you have the same in the front end, and you're just synchronizing the two as efficiently as possible. So most of the work can be done by API calls that involve item ID. So it's always best to communicate via item ID. So you will have your database with your data, and your front end will load the data directly from the database. So it will say, okay, now I need items 17, 24, 29, 35, and I don't know, 25 more, and it will pull that up directly from the database. And on the side, there's going to be a communication that will be, okay, items 17 and 24 are now selected. So you will just fire up a quick call, maybe like using a JSON call that will. I mean, I use them, but I mean you can use post requests if you prefer. That's not. That's not such a big problem, because you're going to be sending only small data, and you're going to say, now I have selected 17 and 24. You send it to the model, and the model will record that, okay, 17 and 24 are selected. And for deselection and things like that, you're going to do the same, and you pretty much do the same for all the operations. But the key is to minimize the amount of data that you send with each request. So it's always good to keep this kind of ID style communication. Don't send images, for instance, with every request, because then it becomes laggy. So it's always best if you have, for example, images, which are or even videos that are pretty much the most taxing data format size wise. Then you're just going to say, okay, this is video 14. You're only talking about 14 in your request. And then when video 14 actually needs to be displayed on the screen, then you will just fetch that from via a URL within your kind of video tag in HTML. So you're never sending the video back and forth in interactive communication, because that would be very, very slow. I hope this example makes sense. If you have follow-up questions, feel free to ask them.
All right, thanks. Then we have another question from Misha. She asks, I have a difficult time understanding what is meant by model from an software engineering point of view. Can it be seen as the model in the model view controller pattern?
Right. So I mean, it's don't worry that you don't really understand what a model is right now, because we haven't actually talked about this yet. I am hesitant to kind of, it's related. I'm hesitant to assign it the equal sign, so like that model equals the model, because the model of in MVC, as I understand it, as I recall it, I mean, it's been a while since I went over this theory, is more about the kind of the application itself. But here, what we mean by model in the visual analytics sense is the part which supports the data, which kind of drives the analytics forward, right? So it might be some structure. So maybe I can give a couple of examples. It can be interactive learnings or semi-supervised learning. It can be clustering. It can be, so we have like clusters. It can even be dimensionality reduction. It's also a model of the data. So we're talking about data models here when we're talking about models in strictly in the visual analytics sense. But of course, if we start designing visual analytics software, then it's exactly right that it starts becoming related to the model in MVC, because we're keeping state of the app and so forth. So we're also taking care of basically variables that make the software run correctly, smoothly, or without errors, right? So there's a bit of a layer on top of the heart, which is the data model that we're actually pulling up towards the screen. But I promise that in the last part of the lecture, I will shed some light on what the models are, at least in the overview sense. I hope this satisfies you. So here we see that the model. Here we are talking about, so it's only coming to existence from the data. So there's a strong tie with the VA model to the data. So we don't see the app node here anywhere. So we're talking strictly from the data point of view. I hope this makes sense, Misha.
Yeah, thanks. And yeah, Lianson asks, for our project, is it sufficient to say that our VA project just shows the data?
Well, no. You need to, like, if you want the queue, so you have to show that you're supporting the user in formulating and supporting their own hypotheses. That's the queue, basically. So just showing the data is so you have to kind of create or let me put it this way. So I don't want to sound too directive here, because I mean it's the TAs that are going to be the main authority judging your projects. But to be on the safe side, what I would do, I would kind of think of the users, what the users or the domain experts of your VA project are, and then you kind of demonstrate with the queue basically that you support the user in formulating and supporting their own hypotheses, and you explain how you're doing that. That would be the correct way, in my opinion.
All right, thanks. And we already have time, but perhaps you want to finish off.
No, it's actually, I wanted to stop, and then I'm going to start about the modeling techniques proper in the last part of the lecture. I'm going to see you in 5. So that's yeah, 38 if I see it correctly. Yes, see you. All right, so let's start with the final part of the lecture, and that is going to be an overview of the actual modeling techniques. We're going to follow the taxonomy introduced in a nice survey from that surveys these methods from a visual analytics perspective. It's an optional reading for this course, but it's a nice pointer to what's there. I mean, at least up to 2017, to the best of my knowledge, there have been no like, let's say, fundamentally interactive techniques that have shaken the world of visual analytics since then. So this still provides a good overview. And basically, what the survey does is it overviews all key modeling approaches that go beyond rudimentary statistical techniques. Even though I mentioned these rudimentary statistical techniques such as mean, average, expected value, mode, median, box plot analysis, the word rudimentary here doesn't mean useless or beginner. It's always still useful, but so use your stats. But on top of that, we might need some more complex ways to do things. Note that the survey mentions machine learning techniques. I don't believe it's a very precise term, so that's why we're going to use the term modeling techniques, which I believe is more correct in this lecture. So there are actually essentially two modeling technique categories. That one is called modify parameters. So that means that your user kind of needs to be a data scientist, and the users are manipulating your model directly. So they are kind of setting the parameters directly, and they're seeing what happens in the system. And this is the easier to implement and therefore the more populous category, but it requires stats and or machine learning knowledge, and it's less intuitive. And the other category, which I think is more desirable, is define analytical expectations. So that means that the user will interact within the domain of their expertise, using their domain knowledge, and the model behaves semantically. So it translates between the user's language and the ML/stat/modeling technique language. There are fewer approaches because it's more difficult to implement. There is a knowledge gap between the developer and the user, and but the big pro and the big payoff is that it's very meaningful and intuitive to the user, and there is no or little knowledge of stats and machine learning required. So this is the table from the paper where we have our approaches classified by whether they're modify parameters or define analytical expectations. And these are indeed the four main modeling techniques, which you might know from your data science and machine learning courses. One we actually know from a previous lecture: dimension reduction, clustering, classification, and regression. So dimensionality reduction as a modeling technique has been motivated in last lecture. It enables visualization of ND data where n is greater than 3. We have been over the techniques, and there are approaches existing for both categories. So you can either you can do semantic manipulations or you can do direct manipulations. The problem is that I'm not aware of approaches for the real top performers. There might be something for TSNE these days, but for UMAP, which is the state of the art in dimensionality reduction, it's still a very new technique. So I don't think that there has been something interactive being done in the world of visual analytics. Next, we have clustering. That's unsupervised learning, where you automatically find groups of data items that are close to each other, or the clusters of data. techniques such as k-means or spectral clustering. There are more. Out of the model categories for visual analytics for the techniques, so we're not going to go over the individual algorithms. This is a high-level overview, and you were always, if you were interested in implementing something in your projects, you are free to search up what you find relevant within the right category. We're just going to do the overview. Clustering is by far the most populated out of the model categories. So clustering is used virtually in all visual analytics systems. I think that it's quite possibly due to the base algorithms being quite mature. So the techniques for clustering are very old. Usually k-means spectral clustering have been here for decades. That's definitely an advantage for adapting it to visual analytics. And I would argue that clustering on the whole, while still very useful, is being overtaken a bit by modern dimensionality reduction methods, especially in general machine learning applications. So there might be a bit more focus on these techniques, but clustering is definitely a good way to go. To give you a couple of examples, so to see the kind of the direct modify parameters version of dimensionality reduction. So here we have a kind of a 2D projection of our data, which is, again, you guessed it, our favorite iris data set. Here we have had some user selections, outliers for Virginica, those with long petals, and you can create new. And here we have this nice side panel with settings. And it's an example of multi-view design. We have a central view with the projection, and we have side panels for control. Here we have a different data set. So we have a 2D projection of countries based on multidimensional data. Here we see a statistical summary of samples in a certain category. So this is statistical summary for Portugal, and we can see highlights of values and the deviations, and also the distribution. We can also, in this 2D projection, we can select two groups to compare them visually. So this will superimpose the Northern Europe distributions on top of South America. We can see the means side by side, and we can see how the groups differ, which can drive our ability to manipulate the dimensionality reduction a bit further, whether it's correct or not. Here we can compare a certain sample, which is selected here and tooltipped with the entire class. It will show the value, it will show the distribution, and also distortions. So here we see those that are marked with the gray outline should actually be closer to the sample because they are closer in the high dimensional space. The white outlined ones are actually further than indicated in the low dimensional space. And here we have another nice technique. So we have projection errors kind of corrected towards the high dimensional for the orange sample. So this is the selected sample, and we see that all of these that are highlighted in gray should be farther in high dimensional space. So they kind of drift away from the selected sample, and the length of the trace indicates the strength of the drift. I think it's a very nice visual summary. And a visual technique rather, sorry. And the white traces are actually directed towards the sample, and those parts should be closer. So that's a nice way to show the stress or the distortion between the high dimensional space and the lower dimensional / manifold space. Regarding the clustering, here we have a nice tool or like this define analytical expectations tool, so the more kind of semantic tool to diagnose and modify clusters. So here we have this kind of flow view where the x-axis ticks are individual clustering, so clustering 1, 2, or 3 that we have achieved on our data, and these kind of bands are individual clusters, and here we see how they flow between the clustering. So we see that this cluster is equal to the same cluster in the second clustering. Here we can see, for instance, that the blue cluster and half of the green cluster flow into from clustering 1 is merged into the yellow cluster in clustering 2. And I mean, of course, you can hover over individual data examples and see the actual instances responsible. And here we see something that like here this effect where an entire cluster gets reshuffled is pretty much that you just assign it a different cluster number. So the cluster stays intact, but here it's been cluster 0, 1, 2, 3, 4. And here it's cluster, or maybe it goes from bottom rather. So this has been cluster 1 here, and here it's been just renumbered to cluster 5, but otherwise it stays intact. And this is, and the authors Turcay and collective show that this is way better than the previous cluster heat maps, where it was that you go along the diagonal. So this is distance between individual points. So the points are on both the x and y axis, and you see that the redder, the closer the points are to each other. So the diagonal is of course fully red because it's the point, the closeness of the point to itself, and the bluer the more distance. And if you have red rectangles surrounded by blue, then you mean that you have quite crisp clusters. So this kind of visualization and this when this introduces analytic manipulations is a way better way to do this diagnose and improve clusters. The further two modeling techniques are classification and regression. Both are examples of supervised learning. In classification, data instances belong to categories called classes. The machine learning model tries to learn these classes, and then it is able to assign an unlabeled data instance to correct class. So recognize an unlabeled car with a brand, for instance. Or for the iris data set to correctly classify the strain for an iris flower. When it comes to the modify parameters, so the kind of direct manipulation category, that is very prevalent in visual analytics. So there are lots of techniques to construct classifiers in the UI, which then will show how well the data is categorized. We are going to see an example in a minute. And the kind of semantic, the semantic interaction category, define analytic expectations, is again a smaller group, like with all these categories, despite there being a very good support for this in machine learning theory. So we have semi-supervised learning, where we are learning to classify many samples by labels for only a few. We have interactive learning, we have relevance feedback, and active learning. So those are where your users are gonna highlight items that they or data instances that they seem relevant, that's relevant or non-relevant for them at the time, which is a very meaningful semantic interaction, and they will get recommendations based on that, which is a very strong way to do DAE classification. But there are still comparatively few approaches for some reason. I don't know why, but you can definitely use these techniques to great success in visual analytics. Finally, we have regression, which is I mean, statisticians will probably kill me for this, but it's continuous classification. We are not predicting a class label, so a category. We are predicting continuous variable, and it's also regression is also used to fit a trend line through the data. And again, there are techniques for both the modify parameters, the direct manipulation regime, and the semantic interaction regimes. Again, going through a couple of examples. So this is Baobab view, where you can construct a decision tree classifier. So here we see that how the data flows from the entry node to the leaves. We see the decision boundaries nicely visualized, and we have some side views to diagnose this tree further. And this is an example for regression, including a video. So if you want to see the system in action, then feel free to go to the video. And yeah, there we are visualizing a distribution of cities' natural gas consumption over feature and feature pairs. So this is an example of regression being used in visual analytics, if you're interested. So this has been an overview of the modeling techniques. So there are 4 categories: dimensionality reduction, clustering, which is an example of unsupervised learning. And then we have two examples of supervised learning, which is classification and regression. Those are your four basic model categories or data model categories related to the previous question, or VA model categories. And the problem, of course, is that adding interactivity and dynamics to modeling, to the state-of-the-art modeling techniques is very difficult, because so if you look at, for example, so where are the deep nets here, right? So that's the modern state-of-the-art classifier for almost everything, and we haven't touched the deep net yet. Well, the problem is that almost all techniques in state-of-the-art of machine learning are static pre-compute ones. So they basically do all the calculation in the data processing slash model construction phase, and they don't think about interactivity that much. Do we have a question?
Yeah, Lianson asks, could you please explain again what you mean with "unfortunately not really for the top dimensionality reduction performers like t-SNE, UMAP, slide 52?
Yes. So what I meant there is that what you see here. So I'm not sure what this projection is, but it's definitely not UMAP, because I'm gonna add a verb to this point so that it's clear. So I'm gonna correct the slides. What I meant by this is that with the modeling techniques, you need to be interactive, right? For it to be visual analytics. So you need interactive manipulation of some dimensionality reduction technique. And these interactive manipulations that are meaningful to the analyst don't exist for the top dimensionality reduction performers. So TSNE and UMAP. So it's usually manipulating ISOMAP, MDS, or PCA, or the older approaches.
Yeah, then I think Lianson also asks, is it recommended and/or common to use both MP and DAE within the same VA system?
Absolutely, yes, you can combine them. And that's a very good question. So all this, what I have introduced, doesn't mean you have to choose exactly one of them. So you're choosing your tasks, you're supporting them somehow, and for each task you might need a different model component. So yes, so think of these as Lego blocks basically, or like building blocks towards your final model. Right. So unless there are more questions, I'm going to wrap up the lecture. I mean, we are running out of time today. So yeah, so we have a plethora of techniques. Many machine learning techniques are static pre-compute ones. They're not dynamic and interactive. So interactive deep nets is still a very open challenge, for instance. And in machine learning, researchers rarely think about interactivity natively. So they consider it a nice thing, but usually it's those models are static ones. So that's why the truly interactive techniques seem to lag behind the machine learning state of the art by 3 to 5 years at least. So, and it's logical, because the technique has to be mature before it can be optimized and made interactive, basically. So, but you can still take a hybrid approach. So you can still, so if you have let's say your favorite deep net that you really want to use in your visual analytics system, what many people do, I do it as well, that you can rely on state of the art in the pre-computing phase. So you can extract top of the line features using state of the art, and then you add interactivity on top, basically. So you will shift the state-of-the-art machine learning to the pre-processing, and then you're going to use other techniques for interactivity, if applicable. So this is also very, very domain specific. And now I have a couple of examples for best papers from the Visual Analytics Science and Technology conference, or track of the IEEE VIS conference. For the sake of time, because I'm not going to be able to go over this in detail. But the point here is that you can see that there's a plethora of domains, that they are all very different, and they have all different strengths and weaknesses. And most of them have very useful demos, for like video demos, so you can see them in action to kind of get a better sense of what a good visual analytics system looks like, at least from the scientific perspective. So those were the best papers at the top visual analytics conference. So there's some value in them. They're very different. I'm not going to go over all of them. So this one is nice visualization of deep nets actually. So this unpacks the model. I think this one is more of a visualization rather than a VA system, but still it got the best paper. So there are more qualified people than me to judge. But I mean my opinion is it's a more of a visualization, but still. Then we have, and there's always like a bit of a text highlight for each of them. What I think is strong about all these systems. So you can inspect this later at your own leisure. This is for a nice tensor representation and model for flow data. 2019 was adding natural language queries. So if you say show speed over time grouped by segment ID, it will create a nice graph for you interactively, which is amazing, I believe. So adding natural language to the interactions. It's like an elaborate kind of filter plus encode interaction. They want that. And then we have the 2020 paper, which is about autonomous driving, and it's traffic light detection and diagnosing why cars fail in some cases, or self-driving cars fail in some cases to detect lights properly. There's a teaser. This teaser is kind of crappy from the science point of view. It's very beautiful, but it doesn't say much. It's kind of like a marketing teaser. But there's, I think, a 10-minute lecture or 10-minute presentation of this if you're very interested. But it's not a mandatory part of the course. This is for you to inspire yourself if you want to. And to conclude the lecture, so the ingredients for a visual analytics system is fundamentally solid visualization, multi-view design most of the time, meaningful support for interactions, and a machine model that takes care of data representations for the visualizations, and efficiently searchable, filterable representation. Representation, singular, to support filtering and exploring, and a hierarchical representation for semantic zooming to support all the seven interactions of E and E et al. Try to support all stages of sense making if you can, but it's a recognized challenge if you cannot support all these arrows in the pipelines. Try to make the model as transparent and understandable for the users as possible. So prefer the DAE category, so the semantic interaction category, over the direct manipulation if you can, but direct manipulation is fine as well. Put yourself in the user's shoes as you design, and this paper provides a very good overview of modeling techniques. Yes, so this concludes the lecture. Thank you. Are there any questions?
Yes, there's a question from Misha. She asks, just to check, a dashboard made with, for example, Tableau that displays data in a multi-view without any ML models cannot be seen as true VA, since it needs some ML-esque model that is interactive.
Yes, so that's a very good point. So there is a bit of a kind of community issue that some of those visual analytics systems are not really visual analytics, but they are labeled as such. And I mean, you have pinpointed a very good example of this, because I personally don't think Tableau is much of a visual analytics system either. But here I'm stuck between a rock and the hard place, because Tableau is considered widely to be a visual analytics system. So I have to teach the community's best practices and standards. But my opinion leans towards Tableau being a bit more of an analytic visualization. So there is a bit of a blurred boundary between analytic visualizations and visual analytics. I wouldn't say that visual analytics necessarily requires machine learning. So that's also why I have corrected on one of the previous slides that you know the survey by Endert and collective talks about machine learning techniques, but not all of them are machine learning. So dimensionality reduction is not machine learning, right? Or it's related to, but you know, a model can be clever statistics as well. So if you're gonna see some of those videos of those papers, not all the models really utilize machine learning heavily. So it's not a necessary condition, but there should be. If I go back to the somewhere where I have the visual analytics pipeline. Yes, so it should be the case that this, whatever this is, should support the visualization and drive the visualization based on the level of knowledge of the user and the stage of the sense making process the user is at. So which is achieved in many cases solely through machine learning, such as in multimedia, as we're going to see in a couple of lectures. Sometimes it can be meaningful stats, right? So this, for instance, if you go over this, I don't think that this way of diagnosing the quality of dimensionality reduction to kind of visualize countries meaningfully on the map, I don't think this has to do much with machine learning, right? So this is just statistics, but it still works, right? It's still a model, so you can still delve deep, and you can drive recomputation of the dimensionality reduction, and you are able to see nice things like this. So this diagnoses the data, gives you insights, and build up your knowledge. So machine learning is not mandatory. It's very helpful, and the lines are blurred, and Tableau could indeed, in a certain sense, be considered an analytic visualization rather than visual analytics system. So that's a correct observation, I would say. So I'm trying to adhere to the standards, which say it's a visual analytics system. I think they market it as such as well. I also think that they're more on the analytic visualization side. I hope that satisfies your question.
Yes. And she also asks, okay, this is a little bit difficult to ask because it's with a screenshot. Perhaps you would want to take a look.
So I'm going to react to that one on Discord then, because I mean we are already running out of time. I would say.
Oh yes, I have to go also. Sorry.
Yeah. So I'm gonna jump to Discord very shortly, and I'm gonna answer all the unanswered questions there. And I'd like to thank you for your attention. Sorry for going over time a bit today, and I'm gonna see you all next week. Thank you.